In this lecture, what we are going to say is d-block elements. First, we should understand why the elements are classified as S block, P block, D block and F block. It's based on the differentiating electron. What is the differentiating electron? Last electron of an atom is known as differentiating electron. Last electron is nothing but differentiating electron. If the differentiating electron enters into S subshell, the element will be present in F block. If the differentiating electron enters into P subshell, the element will be present in P block. If the differentiating electron enters into D subshell, the element will be present in D block. If the differentiating electron enters into F subshell, the element will be placed in F block. Either in any one of the block, the differentiating electron should enter or the last electron should enter. So, D block elements are the elements which as the last electron enters into D subshell. So, the definition for D block element is the element which has the last electron enters into D subshell are classified as D block element. So, we have three types of D series, 3D series, 4D series, 5D series. 6D is incomplete series. Last series is incomplete series. So, we are not going to worry about the 6D series. 3D series is from scandium to zinc. 4D series is yttrium to cadmium. 5D series is lanthanum, then hafnium to mercury. So 3D series is otherwise known as first transition series. 4D series is second transition series. 5D series is third transition series. Why this classification has been done? What is the reason? From scandium to zinc, scandium atomic number 21, zinc atomic number 30. From 21 to 30, the last electron gradually increases in or gradually filled in 3D subshell. From scandium to zinc, the last electron enters into 3D subshell. So scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. For all this element, the last electron for iron 26 electrons are there. The 26th electron is differentiating electron. The differentiating electron enters into 3D subshell. So for all this element, the D subshell is gradually getting filled. Gradually increases the electron in 3D subshell. That's why these elements are present in 3D. Same case 4D, same case 5D. So 3D series is first transition series, 4D is second transition series, 5D is third transition series. Why the elements are called as transition elements? Why the particular name transition series? Because transition elements, there are two ways of defining the transition elements. One is older definition, modern definition. Definition is nothing but the element which are present in between S and P block. In periodic table, hope you remember the periodic table: S block, D block, P block. In bottom of the periodic table, F block. So this is arrangement which was done in periodic table. D block is present in between S and P. So these D block elements are present as in between S and P. They are called as transition elements. Student, this is according to older convention. Older definition is this. What is the modern definition? Elements which has incompletely filled D subshell in neutral state or any one of the common oxidation state. Those elements are classified as transition elements. We will see this. This is a modern way of defining transition elements, and this is a more correct way to define the transition elements. Older one is this, modern one is this. What does mean by this? Element which has incompletely filled D subshell. What does mean by incompletely filled D subshell? D subshell can accommodate maximum of 10 electrons. See, D10 is fully filled D configuration is D10. D10 is completely filled. There is no vacant for electron in D subshell. D0 is there is no electron in D subshell. Other than this two. From D1 to D9. Take scandium. We will see the electronic configuration. Then our next discussion is going to about electronic configuration. If you take scandium atomic number 21, electronic configuration is 4s2 3d1. Here in D subshell it has only one electron. which is not completely filled. D10 is completely filled. D1 is not completely filled. So D1 indicates it is not completely filled and it is transition elements because in neutral state. Either in neutral state or any one of the common oxidations. So the important question is here whether copper is transition element or not. Whether copper is transition element or not. Or zinc is transition element or not. See, whenever you are getting element, you should check in the oxidation state also whether it has completely filled or incompletely filled d-subshell. For copper, we have copper and copper having +1 oxidation state, copper having +2 oxidation state. These are possible oxidation state of copper. Copper, cuprous, cupric. Higher oxidation state is cupric, lower oxidation state is cuprous. Here neutral metal atom, that is copper. Atomic number 29. So here configuration 3d10 4s1. This is for zinc 30. 3d10 4s2. Zinc positive oxidation state is Zn2+. Common oxidation state is Zn2+. So in Cu+1, what is the +1? It loses 1 electron. So it loses the 1 electron from 4s. What will be the configuration here? 3d10. See, here also completely filled. Here also completely filled. But 2 plus 2 means it loses 2 electron. Loses 2 electron from neutral atom. What is the meaning? 2 electron from neutral atom. So copper having 1 electron in S subshell 4s and 10 electron in 3d. So 1 electron will come from 4s and 1 electron come from 3d. So configuration will be 3d9. What about 4s? 4s having 0 electron density. There will be no electron. Now in 3d9 indicates it's not completely filled. D10 is completely filled. D9 is incompletely filled. So copper in Cu2+ it is having incompletely filled d subshell. Because of this, copper is a transition element. Any one of the common oxidant is enough. It need not be have incompletely filled d subshell in all the oxidation state. Any one is enough. Okay, let's discuss about zinc. Zinc is 3d10 4s2. Zinc 2+ means it loses 2 electron. So configuration will be 3d10. So here also completely filled d subshell. Here also completely filled d subshell. Either in neutral state or in oxidation state, the d subshell is completely filled. So zinc should not be considered as transition element. But zinc is a d-block element. So what is the information we are getting? All transition elements are d-block elements. But the reverse is not true. The reverse is not true. What does it mean? All d-block elements are not transition elements. Zinc is a d-block element but not a transition element because for zinc that 30th electron enters into 3d. And what are the things present in zinc group? Zinc, cadmium, mercury. Zinc, cadmium, mercury. Now we have to check whether cadmium and mercury are a transition element or not. For cadmium, the common oxidation state is Cd2+. And the zinc having 3d10 4s2. So cadmium will have 4d10 5s2. So in Cd2+, 4d10. For mercury, there are two possible oxidation states, Hg+1, Hg+2, Hg+2. Mercurous, mercuric, mercury. In 4d10 5s2. In Hg+1, 4d10 5s1. Hg+2, 4d10, that's it. Here also completely filled, here also completely filled, here also completely filled. So what does it indicate? Group 12 in periodic table. In periodic table, group 12 elements are d-block element, but they are not transition element. What is the conclusion we are getting? All transition elements are d-block element, but not all d-block elements are transition elements. For reverse standard, it is very important to know the atomic number up to 30 elements, and it is very important to know the 3D series element. What are the elements? Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Scandium atomic number 21, 22, 23, 24, 25, 26. Now, how to write the electronic configuration? General electronic configuration of d-block element is n minus 1d d subshell of penultimate shell S subshell of ultimate shell 1 or 2. So this is general electronic configuration. Very simple. So we have first 3D series. 3D series means what is the number before the D? What is the number preceding the D? 3. So n minus 1 value is 3. What is the n value? 3 plus 1. N equal to 4. So substitute here 3D 4s. 3D 1 to 10, 4s 1 to 2. This is a general electronic configuration for 3D series. General valence electronic configuration for 3D series. I simply can say general electronic configuration, both are right. Now we are going to use this 3D and 4s to write the electronic configuration for the above element. How we are going to write? The exact way, the real way, it's totally different. Now we are going to write the electronic configuration. For that, atomic number is mandatory. You should know what is atomic number. Otherwise, we can't write. Now, first write 3D and 4s. 3D, 4s. For all the elements, first write 3D, 4s. As of now, just leave chromium and copper. For this two elements, no need to fill the electronic configuration in order. Now, what we have to do is separate this number 2, 1, 2, 1. Here 2, 2. So first 2, 1. What is the second number? 1. So 1 electron will be present in 3D. What is the first number? 2. 2 electron will be present in 4s. Here 3D2, 4s2. Here 3D3, 4s2. Now don't write the electronic configuration for chromium in order. Come to manganese. 3D5, 4s2. Because second number is 5. So second number is the number of electron present in the second number of atomic number is the number of electron present in the 3D subshell for 3D series element. This is all important. First number is the number of electron present in the 4s subshell of 3D series element, atomic number. So here 3D6, 4s2. Here 3D7, 4s2. 3D8, 4s2. Last 3, 0. So 3D10, 0 indicates 10, 4s2. 3D10, 4s2. Clear? This you should be aware of this idea. Otherwise, we can't write the electronic configuration. For 3D series alone, you have to remember it is very mandatory. For other series and all, by using 3D series, you can compare or you can You can write the electronic configuration for other series, but you should know what is the 3D series configuration. For chromium and manganese, if you are following the order the same way, for chromium, what you will write? Second number is 4, so 3D4, 4s2. For copper, 3D9, 4s2. This is what we used to follow. But in real case, what is happening is one electron jumps from 4s to 3D. That will give 3D5, 4s1. One electron jumps from 4s to 3D. That will give 3D10, 4s1. We know half-filled configuration is more stable than partially filled. Half-filled means all the orbital present in the given energy, all the orbital present in the subshell having one electron having the same spin. That is half-filled configuration. Half-filled configuration is more stable than partially. Partially filled means random distribution. It's neither fully filled nor half-filled. Other than this, all the configurations are partially filled configuration. Here 4s is completely filled. Here also 4s is completely filled. But 3D is having 4 electrons. 3D we know it has 5 orbitals. Here it has 4 electrons. On following Aufbau principle, this will be the Boss diagram for chromium. 3D4. 4s will have 2 electrons. Actually this is wrong. We are supposed to write 4s in higher energy, 3D in lower energy. This should be the correct diagram, correct Boss diagram for chromium. 1, 2, 3, 4. Here 1, 2. 4s, 3D. Energy increases in this order. But once the electron from 4s jumps to 3D, 4s will get the configuration 4s1 and 3D will get the configuration 3D. Now S also off filled, D also off filled, D5 is off filled. So the transition, the electron movement is possible, electron jumping is possible. By jumping one electron, both orbital attain stability and extra stability. Compared to here it has more stability. So this is happening. So expected configuration is this, but observed configuration is this 3d5 4s1. The same case here. Here it is partially filled, but here it is completely filled, which will give more stability compared to this. Which will give more stability. So 3d10 4s1. And only one thing we need to remember in electronic configuration is palladium is the only element. Palladium is the only element which do not have any electron in S subshell. All the S electron jumps to the D subshell, and the palladium comes under nickel. Nickel, palladium, platinum. Nickel configuration is 3d8 4s2. What we are expecting for palladium? 4d8 5s2. For platinum 5d8 6s2. Palladium is the only exception of having no electron in S subshell. It has all the electron in D subshell. 4d10. 4d10 is the electronic configuration for palladium. Keep this thing in mind. Okay. Next we are going to discuss physical properties.